All right, today we are diving into one of the absolute coolest, most mind-bending ideas in all of calculus, infinite series. We're going to explore this wild idea that you can add up a never-ending list of numbers and somehow get a single finite answer. So let's kick things off with this big question. Really think about it. If you keep adding numbers forever and ever, can you actually land on a specific value, like, say, the number 2? Your gut probably screams, no way, it's gotta go to infinity. But the answer, which is kind of wild, is sometimes yeah. And figuring out exactly when that happens is what we're all about today. So here's the game plan. First, we'll nail down what convergence even means. Then, we'll get our hands on our very first tool, the divergence test. After that, a super critical warning about using that test. We'll touch on the different flavors of convergence. And finally, we'll see it all work with a couple of examples. Let's get into it. Okay, first things first. Before we can even start testing these things, we've got to have a solid definition of what we're even talking about. What does it really mean for an endless sum to actually have an answer? So here's the official idea, but let's break it down. Just imagine you have a running total as you add each new term. We call that running total a partial sum, or S sub n. Now, a series converges if that running total, as you add more and more terms, gets closer and closer to one specific finite number. It's like it's homing in on a target, which we call S. When you get right down to it, every single infinite series has one of two possible destinies. Either it converges, and that running total locks onto a finite number, or it diverges, meaning the total just blows up to infinity or maybe just bounces around forever without ever settling down. Okay, so that sounds simple enough, right? Well, here's the catch. Actually trying to find that formula for the partial sum, Sn, it's usually super, super hard. Sometimes it's just plain impossible. We need a better way, a shortcut. And that is exactly what convergence tests are. They're tools that let us figure out if a series converges without ever having to find its actual sum. And that brings us right to our first tool in the toolbox, the divergence test. You should always make this your first move when you see a series. Why? Because it's fast, it's easy, and it can save you a whole lot of unnecessary work. The core idea here is actually really intuitive if you just stop and think about it for a sec. If your grand total is going to settle down on some finite number, you can't just keep adding big, chunky numbers to it forever, right? Eventually, the things you're adding have to get so small they're basically nothing. They have to fade away to zero. And this is what that looks like as a formal theorem. It basically says, if you look at the little pieces you're adding, the an, and they don't head to zero, well, there's just no way the sum can settle down. It is guaranteed to diverge. It's a total knockout punch for divergence, which is why some people call it the nth term test for divergence. Okay, everybody, hit the pause button. Seriously, what I'm about to tell you in this next section is hands down the single most important thing to remember about this test. This is where everyone messes up, so listen close. Here it is, in big bold letters. The converse is false. You have to burn this into your brain. Just because the terms of a series do go to zero, it does not, I repeat, does not automatically mean the series converges. This test is a one-way street. It only works to prove something diverges. And if you need proof, look no further than the most famous counterexample of all, the harmonic series. Check out the terms 1, then a half, a third, a fourth. They are clearly getting smaller and smaller, heading straight for zero. The limit check passes with flying colors. But, and this is a big but, it's a proven fact that if you add all these up, the sum actually goes to infinity. It diverges, even though the terms go to zero. So let's just say it one more time so it really sticks. The divergence test can only prove one thing and one thing only: divergence. If you do the test and the limit of the terms is zero, the test is useless. It's inconclusive. It tells you nothing. You got to put the tool down and try something else. Okay, so now that we've got a handle on that, let's talk about the series that do manage to converge. Because it turns out even convergence isn't that simple. There are different strengths, different flavors of it, which is pretty cool. So you've got two main types: absolute and conditional. A series converges absolutely if it still converges even after you make all its terms positive. Think of it as being super stable, rock solid. Conditional convergence is more fragile. It only converges because you have this delicate balancing act between positive and negative terms canceling each other out. Take that away, and the whole thing falls apart. And now for the part that's going to blow your mind. There's this thing called the Riemann rearrangement theorem. And it says something that sounds like it should be impossible. For those fragile, conditionally convergent series, the order you add the terms actually matters. You can literally shuffle the numbers around and make the series add up to any number you want, pi, 0, negative a billion, or even make it diverge. How crazy is that? Okay, that was a lot of theory. It's time to actually see this thing in action. Let's walk through two really clear examples to see how you'd use the divergence test on a real problem. This is where it all comes together. All right, example number 1. We've got the sum of n over n plus 1. What's step 1? Always, take the limit of the terms as n goes to infinity. And for this one, that limit is 1. Now, since 1 is definitely not 0, bam, the divergence test kicks in and we know for a fact this series diverges. Case closed. See how quick that was? Okay, example 2. The series of 1 over n squared. We do our thing, take the limit as n goes to infinity, and this time we get 0. So what does that mean? Remember the big warning? This is where it bites you. It means the test is totally inconclusive. It failed. It tells us absolutely nothing about what the series does. We cannot say it converges, we can't say anything. We have to stop and find a different tool. And that really brings us to the big takeaway question here. We've got this great, simple test to prove something diverges, but what about the other side of the coin? How do we definitively prove that a series like 1 over n squared actually converges? Well, for that, you need some more tools, and that's exactly what we'll cover next time. Thanks for watching.